Okay, state optimization, clear, many of you would have studied. So optimization of unused state. And so these are advanced topics. So if see basically I want to do state optimization. Depending upon the optimization of states, I can realize the most condensed state machine or the use of states, correct? So I can definitely do some sequential logic optimization possible with state optimization. And cloning of logic is done when we are doing a physical aware synthesis. So let's say, for example, I have a piece of logic here. This is some logic. Now this logic is going to, let's say, for example, it's going to a flop, and this flop output is connected through a logic through one place here, and this is also connected to another flop. But let's say this flop is sitting far off. This flop and this flop are sort of sitting far off with respect to this flop. So let's say in my floor plan, let's say this is flop A, this is flop B, and this is flop C. So flop A is sitting here, flop B is sitting here, flop C is sitting here. These are on three corners of the floor plan. So now there's going to be a very large routing delay from A to B. There's going to be a large routing delay from A to C. So to avoid this, what can happen? I can, let's say for example, there is large positive slack available at A. There's a large positive slack available at A. Now what we can do, instead of having A as one flop, we can have A as two flops. So let's say since there's a large positive slack available here, this is this logic. I will call this as logic A prime A, or let me call this as logic A1. So this is the logic A1. The logic A1 is going now to two flops. And now this flop is connected through this logic to flop B, and this flop is again connected through this logic to flop C. So I now have two copies of A. So since now I have two, since I have a huge positive slack in A, I have no problem. I have two sets of A now kept here, driving the same input. Now the timing path will be only from B to C, because I have a large positive slack in A. Even though I have to travel some extra distance to come till A, that's okay. So this path of the logic will meet the timing. This is my new A, and okay, two copies of A I will have, and now I will be able to meet timing from A to C also and from B to C also. Okay, and another sort of logic, another concept is called as retiming. Let's say for example, I have a logic like this here. These are not straightforward techniques, these are advanced techniques. Let's say for example, the combinational logic here is say 5 nanosecond, and the combinational logic here is say 2 nanoseconds. Okay, now let's assume say clock to queue delay and setup time is approximately 0. So we don't even consider. So what is the maximum clock frequency of this circuit? All these are getting the same clock. Now if I look at this portion of the circuit, you may say that I may clock it as good as 500 megahertz, correct? Because it's having only 2 nanoseconds delay. Whereas this portion of logic, you may say that you can clock it only at 200 megahertz. So effectively, these two, effectively, I will be able to clock at only 200 megahertz. Correct? Now let's say for example, I do something like this. Some portion of the logic here, I shift it here such that This is around 3.5 ns. So overall combination delay is 7 ns, right? So now I'm sort of splitting the logic more equally. This is 3.5 ns, this is also 3.5 ns. Or let's say I may not be able to slice it exactly 3.5 ns. Let's say this is 4 ns and this is 3 ns now. Now if you see, this portion of logic will be able to work at 250 megahertz, and this portion of the logic will be able to work at 333 megahertz, correct? So effectively I will be able to work at 250 megahertz, which is minimum of both. So 250 megahertz. So a circuit which was working at 200 megahertz, by partitioning the logic. So what I did was, effectively some portion of the logic here, I sort of removed it and pushed it here. So this logic increased because I have some useful slack here. When I'm going to clock it at 200 megahertz, I will have lot of slack here. 200 megahertz is 5 ns. So when I'm going to clock it at 5 ns period, there will be lot of slack here. So I'm sort of eating away the slack here and sort of trying to reduce the delay here, so that I can increase the frequency of operation of the circuit. Thereby, let's say I'm not able to exactly sort of slice it through, but let's say I'm able to push some of the delay from here to here. Let's say 1 nanosecond of delay I pushed from here to here. Some logic I moved from the flop here to the downstream of the flop, such that this delay is now 4 nanosecond and this delay is 3 nanosecond. So effectively I will get 250 megahertz of operation. So this is a retiming is a technique to improve the performance of the circuit. See, a circuit which was able to work at 200 megahertz, we are now pushing its performance to 250 megahertz by retiming. Okay, this is a very interesting concept. Here we are playing with the useful slack to get the benefit of performance. Okay. So all these are advanced topics. So these are just, I am sort of giving as a tips to you for your preparation, but these are not covered in labs. We cover the basic sequential constant optimization in labs. Okay. Thank you.